All right, let's go ahead and take a look at page 3. I'm going to hold off on number 9 for a separate video because I just want to take a little extra time on that one and really focus on it. I find that one a little bit more challenging than some of the problems. So anyway, let's go ahead and take off on problem number 8 then. So right off the bat in this question, you'll notice the statement actually tells me about the similarity values between these two things, that TRS is in fact similar to TQP. So one of the things that I have mentioned to you guys in the past is that sometimes it's a really nice idea when you have overlapping triangles to separate those triangles. And so this is TRS that they mentioned, where this is an 8 and this is a 17. And then I have this other one over here, which was T, Q, and P. And I know that this is 24. Now, one of the things that might help you see very, very quickly is, do you see that there is a 3-to-1 proportion between these two triangles? So whatever side this is 3 times as big. That's actually kind of helpful. So right away, I can indicate that if this is 17 and there's a 3-to-1 scale factor, then 17 times 3 is, of course, 51. You can't see that because the glare on the screen. That's 51. So I know the side QP down here is 51. That's pretty nice. Now, unfortunately, we got ourselves a little bit hung up on the next little piece, but there's some really nice little strategies that are buried within these as well. Because if these are similar triangles, that means these angles right here are the same, right? And these angles are the same too, which means these are parallel. And we had a theorem that we actually went through and proved called the side splitter theorem that actually says not only are the entire sides proportional, so are the pieces. So internally, what you could see is an internal proportion. Notice this is a 2-to-1 proportion internally, that this chunk is twice as big as that side. So if that's true over here, if this is in a 2-to-1 proportion, then this is also in a 2-to-1 proportion, which means this side is 15, which means this entire side is 45. And that makes sense because it should have been in a 3-to-1. So the value of TS is in fact 15. Nice, easy little problem. Like I said, we're going to hold off on number 9 for a later video. Now, in this one, it says, let's find the length of that. And so we already know that they are similar because of the angle-angle theorem. And so now we can just look at our proportions. And I could say that the proportion of 6 to 12 should be the same as, now 6 is the one between the single and the 40, so the one that corresponds to that angle A, but the side between A and B, should be the same side over here. But notice between the single arc and the 40 would be x minus 3 and x plus 1. Now, this is a personal preference thing. When I see a problem like 6 over 12, I immediately am going to reduce that fraction to make my life just a little bit easier, although you could use the larger numbers and you'll get the same answer. I just prefer to simplify. So if I cross multiply, 1 times x plus 1 is in fact x plus 1, and 2 times x minus 3 is, let's see, that would be x plus 1 equals 2x minus 6. So I think what I'm going to do is I'm going to subtract x from both sides. I kind of ran myself out of room here. So I've got 1 left over here because the x is canceled. 2x minus x is x. And then if I could add that 6 to both sides, I've got x equals 7. And although I know a lot of you would do that and just walk away from the problem, we're being nice to you by asking you to find the length of those missing sides. What is ED? Well, let's look out. If I plug in 7, then 7 minus 3 is in fact 4. The length of ED is 4. I'm going to put a 4 right here. And if I plug in 7 right here, 7 plus 1 is 8. Now, you may not really realize why I'm saying that's nice, but there's all these nice little proportions. Notice the short side is half the length of the long side. Is that also true here when we did our work? Is there a nice proportion that the short side is half the long side? It is, right? And so you could kind of see that that means what we did makes sense. So within the own figure, it's a 1-to-2 ratio. This way also works as well. You could also see that there's a scale factor between the two of these things that this side over here is 1.5 times as big as 4, and 12 is 1.5 times as big as 12. So you could see an internal scale factor that way as well. Now, same thing over here. Because these are parallel lines, we could say these angles match. We could say these angles match. We know they're similar by double A. And what I notice right away is I see a scale factor of 4-to-1, right? So this side is 4 times as big. So depending on how you want to do that, we could say that the parallel side is to its partner right here, as the parallel side is to its partner. And it's really important that you make sure you line these up right. So I know that this matches because it's between what I mark as a single and a double, and this one is also in that same location. The 18, or I should say the 16 that I have right here is right on the other side of the single arced line, a single arced angle. So we're looking pretty good. Now, if you had picked a different ratio, we could have probably done a little bit better, but when we cross multiply 16 times x and 16 times 3 would be the same as 4 times x and 4 times 18. Now, over here, I showed that distributive property, and over here, I kind of skipped that. But if it helps you to show that it was 16 times x minus 3, being 4 times x plus 18, and then you did the distributive property, that's okay too. All right, so I'm going to subtract 4x from both sides. I got 12x minus 48 is equal to 72. I'm going to add 48 to both sides. And now I've got 12x equals, let's see, what is 72 plus 48 is 120. And what do you know? That was so nice. I got x's exactly 10, right? So it says solve for x. So I got that x is 10, and my scale factor is 4-to-1, or you could say 1-to-4. So depending on if you're going from little to big or big to little. So if it's little to big, it's 4-to-1. If it's big to little, it's 1-to-4. And of course, our last little thing, a little SOHCAHTOA, right? Little trig, SOHCAHTOA. We'll kind of finish off page 3. So the tangent, this is telling me to stand at the tangent here. And the tangent is opposite over adjacent. Now keep in mind, this is always going to be the hypotenuse no matter what. That's 100% true. The tangent is 40 over 9 because the 40 is far away and the 9 is close. Opposite is far away, that's close. Whereas the cosine should be the close one divided by the hypotenuse. So the hypotenuse we already established is 41. And when we're standing at A, the 9 is very close or adjacent. Now, if we switch over to C, when I first did this, I kind of messed it up because usually we make the right angle C, but I kind of messed with myself even when I wrote this question. So the sine of C, it says, now let's go over here and stand at C. And let's find what is far away from C, which of course is 9. And the hypotenuse we already established is this. And that makes sense that because these two angles right here are complementary, A and C are complementary, the sine of one is the cosine of the other. And we had a problem like that in our homework. And last, the cosine of C means I would like the adjacent one to C, and I'd like the hypotenuse. Remember, cosine is the adjacent or close divided by hypotenuse. Not sure why all this stuff showed up in my copy, so it's made it a little hard to read, but hopefully we can do it. So notice the hypotenuse is not used in this problem. I never had a hypotenuse, so it can't be a sine or a cosine. It has to be a tangent. So the tangent of 40 degrees, remember, is defined as the opposite over the adjacent. Now, this is a little bit of a bummer because when we do the tangent, notice the variables on the bottom. That's not my favorite thing. So the tangent is 0.839, 0.839. So if I cross multiply, 0.839 times A is equal to 7. And so what I need to do is I need to take the 7 that I have and I need to divide it by the 0.839. But I'm not going to type it. I'm going to use 7 divided by the answer. Remember, the answer on our calculators are always sitting above that negative sign. And so I got 8.34. So A is 8.34. Now, one of the things that we talked about, at least in my class, and maybe other classes did as well, because there's 180 in a triangle, I know that that missing angle was 50. I didn't need that angle, but what I noticed is we had a theorem last semester that said opposite, the larger side is the larger angle, and smaller sides are opposite smaller angles. And what I noticed is 40 is opposite 7, 50 is a slightly bigger angle. And what do you know? It's opposite a slightly bigger side. So that actually sounds good, like my math makes like sense. It probably is okay. Now here, we're going to be looking at a cosine because the cosine is the adjacent, the close one, divided by the hypotenuse. Now again, this is just like this one where the variable's in the bottom. That's kind of the bummer. Cosine of 64, we're looking at 0.438. I'm going to cross multiply. 0.438x is 15. And so I just need to take 15 and divide it by the cosine of 64. And I got 34.2. Now keep in mind, the hypotenuse has to be the longest side of any triangle. But also what I can tell you is if this is 64, then this angle down here is 26. Well, 90 is a much bigger angle than 26, and so that makes sense that 34 is a much bigger side than 15, so it plausibly makes a little bit of sense. And so notice we had a tangent here and a cosine. This should not surprise you. If we have a tangent and a cosine, we're going to have a sine. So this time the sine of the angle is opposite. It's far away divided by hypotenuse. But this time we need to do the inverse because I'm looking for the angle. So what I need to do is I need to take the sine inverse to find that angle. So I'm going to hit sine inverse of 13 over 27. And I got 28.8 degrees. Okay, 28.8 degrees. Now, remember, we have talked a little bit about how we have our stuff right here. So you can always use these charts as well. Like we said, the tangent of 40 was 0.839 and it's sitting right there, 0.839. You could get the same information off of these things. On this last problem, I said the sine was 13 over 27. The sine was 13 over 27, which is 0.48. So if we look for the sine, which is this top one, and we look for where that says 0.48, as I slide on down, 0.48, 0.48, right around there, somewhere between 28 and 29, but a little bit closer, looks like to me, to 29 than 28. So made 28.7 or something like that. And you'll notice that's actually fairly accurate when I just kind of guessed at it. So hopefully that was helpful. Thanks for joining me for a few minutes. I'll see you guys back in class. Bye.